Welcome to the deep dive. You sent us a really fascinating topic, 3D printing, and wow, a ton of information to explore.
Yeah, quite a bit.
Our job really is to unpack it all for you, pull out the most interesting bits, the useful insights, without getting totally bogged down in the super technical stuff.
Think of it as a shortcut, yeah, to getting a real handle on what this is all about.
Exactly. So today, we're diving deep into 3D printing. The resources you shared, they give us this really broad view, right? From its surprising history to the materials.
Oh, the range of materials is huge. And the ways it's being used, it seems almost endless.
So our mission here is pretty clear. Make 3D printing understandable, engaging for you. We want to talk about the unexpected bits of history, explain the text simply.
And find those moments that make you go, aha! Connect it back to how things are made generally, where innovation is heading.
You've given us a lot to work with, seriously.
Yeah.
So let's jump in.
All right, let's start with the basics. What is a 3D printer? Fundamentally, it's a machine, controlled by numbers, kind of like a robot, yeah, with a tool attached.
And the key part, the 3D part, is that this tool usually works in 3 dimensions to, well, build things, objects.
And importantly, your sources point out this tool generally adds material, layer by layer.
Right, which is different from, say, CNC machining, where you carve away material from a block.
Exactly. Subtractive versus additive. Though the material you sent does hint that we might see more hybrid machines down the line. Ones that can do both.
Interesting. And you mentioned it's like a robot.
Well, yeah, a numerically controlled machine is a type of robot.
Yeah.
And robots come in all shapes and sizes, some moving in like more than 10 different ways, 10 axes.
Wow.
But the real secret sauce, according to your sources, is the tool itself. What tool is actually being used?
Okay, let's dig into that. The key being the tool. The info you provided really hammers this home, how much that tool affects what you can make, its capabilities, the materials.
Everything. From working way down at the atomic level to shaping clay to using all sorts of, synthetic materials.
But it's also crucial to remember, as the sources point out, every tool has limits. It can't do everything.
Precisely. And to really get where 3D printing is now, it helps to glance back at the history of what your sources call manufactured control. For ages, making stuff needed tons of manpower.
Oh, absolutely. Think about building anything complex back then. So much effort, so many people. Then we got simple tools, levers, wheels, giving us a mechanical advantage.
Made things easier, more effective, led to gears, more complex machines doing jobs hands used to do.
So when did the control part start to get automated?
Well, the sources flag some early examples. Basil Bouchon using punch paper cards for looms way back in 1725.
1725.
Yeah, and Jacques de Vaucanson experimented later. But a big leap was Joseph-Marie Jacquard's programmable loom in 1804. Used long tapes with instructions.
Okay, punch cards, tapes. This sounds familiar.
Right. And apparently people resisted it at first, but eventually those looms were everywhere.
And this idea, programmable instructions, it carried on into early computers, didn't it?
Absolutely. Your sources mention Conrad Zeuss's V1 computer in 35, using punched film for its instructions, and his later V3 in 41. So telling machines what to do step by step, it's not a new concept.
Okay, so how does this connect to 3D printing emerging?
Well, the sources talk about this new thought in manufacturing around the 1930s. The idea of building things layer by layer. That's the core of 3D printing.
And it seems it's had a lot of different names over the years.
Oh, definitely. Additive manufacturing, rapid prototyping, even manufacture anywhere shows how people have looked at it from all sorts of angles.
Got it. So building in layers, machine control. Now, the info you sent has this incredibly detailed list. Manufacturing technologies and techniques. It really puts 3D printing in perspective, doesn't it? Part of a much bigger manufacturing world.
It really does. The variety is just striking. You've got everything from like hand-powered stonecraft livers, chisels, right up to super advanced control systems, multi-axis machining, complex software.
And the ways to actually shape materials. Milling, lathes, plasma cutters, lasers, fusing materials together, working with ceramics, metals, plastics.
And then there are all the molding techniques, thermoforming plastic sheets, injection molding for detailed parts, even rotational molding, which surprisingly works for plastics, but also like chocolate.
Chocolate molding. Okay. So where does additive manufacturing, 3D printing fit in this picture?
All right, the core topic. Your sources list a truly mind-boggling range of additive methods. Binder jetting using liquid to stick powder together. Material jetting depositing tiny droplets.
And then the one most people probably picture, extrusion.
Yeah. FDM-fused deposition modeling. That's your typical home 3D printer, often, pushing out melted material. And it handles a huge range of plastics, obviously, but even edible things, Clay.
And that's just scratching the surface based on this list. Powder bed fusion, sheet lamination, directed energy deposition, electrochemical deposition. It sounds like there's a method for almost anything.
Pretty much. Using light to solidify liquids, different powder techniques, that continuous liquid interface production. The upside-down printer one sounds very sci-fi.
It really does.
And it gets so specialized. Techniques for specific powders, for making braille dots with UV glue, metal printing using electric fields.
It just keeps going.
Oh, yeah. Direct writing, liquid phase printing, valve-based printing for biomaterials, two-photon polymerization for incredibly tiny things.
It's almost too much to take in. And then the sources even mention fabrication methods that take stuff away, or mix approaches, particle beams, lasers, water jets, even papercraft for prototypes.
Right, and then you get into the really high-tech stuff like nanolithography, making things at microscopic scale.
It feels like we're constantly heading towards more control, more precision, smaller and smaller scales.
Definitely. And the sources highlight some seriously innovative additive stuff too. Magnetic fields for bioprinting, robots made of reconfigurable modules, even swarms of little robots printing things together.
Robot swarms. Okay, and then, just when I thought it couldn't get wilder, direct print manufacturing with tiny pumps. Claytronics, using biological systems like ribosomes.
Yeah, programmable matter, basically. And using bacteria, directing silkworms, printing cells. It even mentions using diatoms, those tiny algae and their byproducts.
Technology and biology are really starting to blur.
They really are. And to drive home the point of what's possible, the sources list a sample of things that can be printed. And it's everything. Toys, lights, buildings, medical aids, even weapons.
Okay, that's a perfect lead-in. If you can print all that, what are you printing it with? The 3D printable materials section. The sources make a huge point here. Basically, with the right printer or process, you can print almost anything.
Which opens the door to totally new material combinations, stuff that doesn't exist naturally.
So we're not just talking basic plastic.
Not at all. The list is incredible. High-tech metals, precious metals, silver, gold, platinum, even green ink, soil, water, seeds that can actually grow.
Grow. That's amazing.
Isn't it? Then biological cements, fibers, and yes, the common plastics like PLA and ABS, but also versions mixed with wood, bamboo, bronze, copper.
More specialized stuff too. Nylon, flexible materials.
Yep, Benlay is mentioned, PCL, bioplastics made from plants. Your sources even give recipes for starch-based ones.
Recipes.
And the biological side is fascinating. Printing stem cells for skin, PVC, different cements and concretes, huge potential for construction, medicine.
What else? Epoxy, rubber, silicone, sugar. Even sugar and chocolate for food printing.
Right, edible creations. And gets more advanced, printable sandstone you can dye and seal, complex inks, glass, even special glass inks for lenses.
High-tech materials too.
Oh yeah. Graphene mixed with plastic for batteries, coatings, shape-changing materials, hydrogels materials with graded properties.
Graded properties, like different characteristics in different parts of the same object.
Exactly. And think about printing metals that melt at specific points, alloys for joining things, materials that change shape on command. That's 4D printing. The possibilities are staggering.
Paper pulp, magnetic materials, carbon fiber, both as filament and as a coating. It's just...
wow, the variety.
It really is astonishing.
But, okay, reality check. With all this potential, there are still hurdles. Your sources talk about learning, access, and limitations. It's not quite push-button simple yet.
No, definitely not. There's a learning curve. The design software, the printers themselves. The sources even suggest that familiarity might vary, geographically.
And getting your hands on the really good printers, still tough for many. Hobbyists often have the extrusion types, which have limits.
Right. Using online services for fancier stuff, metal printing, etc., can be pricey, might have size limits, and raises questions about protecting your designs. Who owns the file, the process?
And the sources are pretty blunt about the current 3D printing disadvantages. What are the main ones?
Well, speed, it can be slow. Cost printers can be expensive up front. Materials still not as wide a range readily available as traditional methods. Energy use can be high.
Quality issues, too. Sometimes. Strength might not be the same, depending on the print. Often needs post-processing, sanding, finishing. Build size is often limited, or you lose detail going big.
Complex designs can be tricky.
Yeah, really intricate shapes need serious computing power. And then environmental stuff fumes, waste from failed prints, powder mess with some techniques. Plus that learning curve we mentioned. Software and hardware can be complex.
And there's a special note about always weighing the cost and time, right? Just because you can print it doesn't mean it's the best way,
Absolutely critical point. Efficiency matters.
which leads right into waste. What about reuse recycle efforts? People worry about material costs and leftover plastic, right?
And rightly so. But the good news is, people are working on it. Your sources mention ways to recycle waste back into usable material, using heat, even microwaves, to break stuff down. Biological decomposition for some materials, too.
And specific techniques.
Yeah, recycled deposition modeling. Basically grinding up waste plastic and extruding it into new filament. There's even a project mentioned, AAMAZ, focused on zero waste for metal printing. And we get a list of melting points, gives you an idea of the temperatures involved.
Okay, so to understand that common extrusion printing better, your sources give a list of extrusion 3D print terms. Helps decode the jargon.
Definitely. Explains basics like extrude, parts like the hot end, nozzle, the extruder itself that handles the material, important settings like extruder temperature, layer height.
Things that affect the print process, too, like the layer fan for cooling, infill for internal strength, the print bed or build plate where it happens.
Even terms like frog for those stray bits of plastic. And the starting point for any build, the bill of materials, the bum-bum.
Now, actual examples of 3D printers. The sources start simple with the 3D pen.
Right. Very direct, but slow, maybe uncomfortable, potential fumes. Limitations.
And then the MakerBot.
Described as a commercial take on the open source RePrap project. Shows that. Open source to commercial pathway.
And the Delta Tower.
Highlighted for printing big things and using special silkworm software for cool woven patterns. It also notes how different brands might just be variations on similar core tech.
That brings us to understanding the basics. And here, the sources make a really cool comparison. A 3D printer and an embroidery machine.
Yes, insightful. Both are essentially CNC machines controlled by numbers. Embroidery works in 2D, following machine code. Instructions, move here, use this thread, make this stitch.
And machine code is super basic computer language, right? Just above binary. We even get a G-code sample.
Exactly. And digitizing in embroidery, turning an image into machine points, is pretty similar to turning a 3D model into the printer instructions.
The link to plotters is interesting too.
Very similar components, right? A base, motors, belts, a tool holder, controls. Plotters draw or cut, printers build up, but the underlying mechanics share a lot. They have their own languages too, like HPGL2.
And you can modify plotters.
Apparently. Use different tools, etching, hot wire cutting. There are even robotic plotters, including a wild water plotter using water jets and light.
All these machines need to know where things are. Coordinates, spatial reference, and computer vision.
Crucial. The sources note that programming this needs spatial awareness, both from the human and the software. And maybe we lose some manual skill as automation increases.
Makes sense. It explains the standard coordinate systems, 2D, 3D, 0 point, how motor size and gears translate to movement. Tool size and resolution affect detail.
And being able to set your own starting point, the origin, is key. Spatial reference systems minimize distortion.
And the future is computer vision, the machine watching itself print.
That's the potential. Real-time monitoring, error correction. But it's expensive, not common yet. Your sources list some spatial data formats too.
Okay, so before building a printer, the sources say, first, build your own robot. Decide what kind you need.
Right, purpose dictates design. And the list of typical types of CNC robots is extensive. Stationary, serial, parallel, mobile robots for different terrains.
Robots for hazardous places, robots with different levels of autonomy, different degrees of freedom or movement. Linear robots, gantry or Cartesian, the common 3D printer types.
Cylindrical, spherical, articulated arm robots, scare robots, multi-axis ones. It's a whole field.
And lots to think about when building one. The considerations list is long. Axes, workspace size, kinematics, payload, speed, accuracy, power, sensors, waste, cost, plus software to run it all.
So let's focus on the common type. Building a Cartesian robot-based printer. Often cheaper, sources say. What are the main components?
Structure first. The frame, the build plate, fixed or moving. Then movement parts, usually a motor per plane, maybe belts, encoders to track position.
Then the tool interface to hold the tool, and the tool itself, typically that extruder, with heating, dispensing, cooling parts, maybe a fan.
Electronics next. Control board, like a breadboard initially. Computer, power supply, limit switches to stop movement, and fasteners, screws, nuts, bolts. Sources note some parts are optional, materials vary widely.
And if you don't want to source every part, packaged kits exist. Piccolo, RepRap, raw stock. Several options listed.
Even Lego-based 3D printers. using Legos for the frame with hot glue or pancake batter extruders, or combining Legos with printed parts.
Fun, but there's that special note. Again, be wary of crowd-funded hardware that might never materialize.
Good reminder. Sources also mention linear actuators as an alternative to belt spoolies. And finally, the firmware packages, the brain software like Marlin, Smoothie, or Ball that actually run the printer.
Okay, structure, motion, control. Now, at the heart of it, build your own tools. Extruders is most common, sources say.
And the concept is surprisingly simple, right? Goes back to baking. Pastry bags, dough dispensers.
Exactly. Pushing material through a nozzle. Hand-powered, then electric. The sources mention an 80s cookie maker example. Plunger, screw, gears, viscosity, how thick the material is key.
And there are links for building other tools, paste extruders, other CNC tools.
Yeah, resources are out there.
And whatever the tool, you need a surface. The build plate, what's it made of?
Lots of things. Special glass, regular glass, often heated, plywood, tape, old CDs, acrylic, fiberglass, steel, aluminum, stone, sheet metal. Sources even describe one for a sewing machine. Versatile concept. Get hardware sorted. Now software, the instructions. Sources explain how high-level code gets translated down to machine code. For 3D printing, there's that extra step, turning a 3D visual model into machine instructions, often G-code.
And there's software for making the models.
Loads of it. The list focuses on free downloadable tools. Blender, FreeCAD, OpenSCAD, many others, plus tools for just viewing or managing models.
And the file formats, we see common ones like .stl, .dwg with their origins, but converting between formats can lose data.
It's a risk, yeah. Things can get lost in translation.
So once you have the model, how do you actually tell the machine what to do, controlling the machine? Sources talk about APT first.
Automatically programmed tool system. An early effort using English-like words translated to numbers, kind of like how web addresses work, came out of a U.S. Air Force project.
And then the main one today. G-code.
Right. Most common CNC language. Lots of variants. But efforts towards standards exist. It tells the machine where to move, how fast, what path, specific actions.
But it's limited. Not much logic.
Pretty much. Basic commands. Sources predict more advanced languages will eventually take over.
We get the G-code format. Examples of tools like M for milling, letter addresses for axes, A for rotation around X.
And a selection of actual G-codes. G00 for rapid move, G01 for controlled linear move, M03, M05 for spindle on-off, plus a ton of other related CNC terms.
For working with G-code, there are G-code editors. Even basic Notepad works, and software that generates it automatically for models.
Yeah, those are the G-code generators, often called slicers. SlickThread or Cura are popular examples.
Yeah.
They do the basic job, but maybe without super fine control. There are also specialized tools listed for gears, engraving, cutting.
An historical tidbit about early German computing investment.
Yeah, interesting side note there about the Planck-Ockel language.
Okay, shifting gears. What if you have a real object and want a digital model? Capturing the physical world via optical scanning.
Right, reverse engineering. Lets you replicate things. Leads to that joke. Can you 3D print a 3D printer?
Ha! But scanning only gets the shape, right? Not the function.
Exactly. To improve something, you need to understand how it works. Sources describe different scanning methods, cross-sections, whole-body color scans, even DIY setups with lasers and cameras. Open-source software like ScanRate exists too.
Taking it further, blending real and virtual with augmented reality. The Luminar bulb example.
Yeah, projector, camera, computer, all in one. Overlays digital info onto real objects, lets you interact with gestures. Could be huge for manufacturing guidance.
Now for the fun part, the sheer range of stuff you can print. That list of assorted printable objects is wild.
It really shows the scope. Unique components like a cardan suspension, a working music box, construction blocks, connectors for furniture.
Printable chainmail, a switchblade, just the blade. Even open source weapon designs.
On the practical side, a mini loom, a print head for a knitting machine, an open source siren, an EEG system for medical research, even a model skeleton.
Medical applications seem big. Prosthetics, open source leg and dental models, even a concept for a full-body exoskeleton.
Transportation too. Unicycle design, snow machine, electric car, drones, and real aerospace applications. Airbus printing parts. China using it for their C919 jet. Plus, just making replacement parts for things.
Power generation wind turbine designs, computer parts, Raspberry Pi cases, fan ducts, even a mechanical computer design.
Tooling wrenches, looms, ring sizers, art 3D model of an ancient relief. Buildings, open source steel design, even tattoo machines and a modular phone concept.
But again, the caveat, Some models are just surfaces. Making fully working things depends on materials, tools, cost.
Exactly. And there's a massive list of model libraries where you can find these designs online.
Okay, moving beyond just single objects, what about printing complete systems?
Big advantage here. Multi-material printing without assembly. The source mentions this futuristic shoe concept. Sensors, power, computer, lights all printed together. The tech exists, mostly.
And the truly grand vision, the complete building construction system, an airship printer.
Yeah, imagine an airship with multiple print heads fed by different materials building everything from the ground up, even furniture. Wild concept.
Flying printers are already being tested, right? Small drones building things.
Right, projects like flight assembled architecture using drones and foam bricks. Great reach, but payload and accuracy are challenges. Maybe good for tensile structures.
Managing building data needs special formats. BIM, OpenBIM, and software. We see examples of construction automation too. Bricklaying machines, 3D concrete printing.
The design-to-operation idea is key sharing data through a building's whole life. Sources mention a traditional Chinese structure as a historical example of self-containment. The author even envisions a complete roadway construction system. Large build formats enable huge, detailed mechanisms.
This all points towards the factory of the future, and it's not entirely new.
No, industrial use is the longest-standing application. Sources cite a 1977 program on integrating computers in manufacturing. Even DARPA plans from 2011 talked about revolutionary 3D printing and self-replicating materials.
The Instant Foundry Adaptive Through Bits concept fits here too, and that video game War Factory, early popular idea of rapid production.
The core idea of machines doing labor for human benefit is old. Sources contrast machine versus non-machine traits, consistency, quality, cost, but also potential errors. Examples like military drones or surveillance robots show automation replacing human roles.
But there's a counterpoint, the non-machine machine.
Yeah, the perspective that cheap labor in some places might be a bigger disruptor to jobs than automation itself currently.
All this change implies a shifting infrastructure, doesn't it?
Foreseeably, yes. A move towards uniform data formats to cut waste and inefficiency. Japan's use of lightweight 3D formats. Industry systems like Kitaya, JT steps in that direction. Mostly CAD outward now, but reverse engineering scan to CAD is also happening.
Which enables mass customization, tailoring products.
Exactly. Instead of one-size-fits-all mass production, personalized medicine, bespoke fashion. Those are existing examples.
Could this replace traditional retail, on-demand, custom manufacturing, consumers making their own stuff?
It's discussed as a possibility. The idea of manufacture local becoming the new buy local.
So how are people actually monetizing 3D printing today?
Mostly the print for pay model. You order custom items, jewelry, fashion, hobby parts from a third party. Novelty items are common. Hobbyists experiment. Larger formats for education, art, small commercial runs, private contracts.
Large-scale manufacturing isn't quite there yet.
Not commonly, no. Likely to be hybrid approaches for a while. Print on demand helps small businesses, but competing with traditional manufacturing on cost and awareness is hard.
But individuals and open source are driving lots of innovation. The open source DIY project section is huge.
Really empowering. Open source cell phone design, furniture systems, open structures, chair design software, even making a playable record from digital music.
Bioprinting at home.
DIY bioprinter projects exist. Inkjet shields for Arduino, open source PCR machines for science, construction methods to compress earth blocks, sustainable concrete alternatives, even rammed earth techniques.
And space projects.
Open source satellite design, spacecraft projects, and that amusing wake and bake printer name again.
Finally, looking ahead, development concepts, pushing the boundaries.
In electronics, printing components, biomimetic materials, quantum dot LEDs, clothing, embroidery tools, concepts for printing garments.
Medical seems massive. Printing tissues, soft biorobots, advanced prosthetics, web-customized hands, enable. Yeah. Surface texture is key for medical devices.
Exoskeletons for assistance. Bioprinting, actual human tissue, organovo. NASA exploring printing biomaterials in space. Buildings, printed houses, concepts for extraterrestrial structures.
Transportation, local motors, printing cars, downloadable Honda models, even toys with universal kits. Art via robot taggers, graffiti languages.
Farming robots, FarmBot. Food concepts, digital gastronomy, printed gum, airplane food ideas, power, printed turbines, atmospheric motors, manufacturing, manipulating materials with sound, personal nanofactories, mobile automation, and distribution via the Internet of Things.
But with all this creation comes intellectual property rights, the big dilemma.
Benefit for all versus profit for the creator. Sources lay out arguments for IPR incentive, innovation growth, and arguments against or negative consequences, slower innovation, limited access, higher costs, stifled creativity, enforcement issues, potential abuse, impact on developing nations.
It's complex. Where things even come from isn't always clear. Need honest info. Sources list ways to spot likely infringement, but with caveats.
And protecting the digital files themselves is a challenge. DRM and such exist, but software limits are hard to enforce, especially with custom or older machines. The example given is concerning.
Okay, let's end on a lighter note. Making it fun. You don't always need complex software. Punch cards.
Yeah, like the old looms,
Yeah.
still used industrially. The idea is you could create punch cards with binary code, build a reader, very hands-on.
And using printers for art, music.
Translating music into G-code, make the printer play the song through its movements. There's even a MIDI to G-code converter online mentioned.
We get a G-code snippet for Flight of the Bumblebee. And links to printer music examples like dot matrix printers making sounds. Similar idea.
It shows the creative potential beyond just making objects.
Wow. Okay, what a journey that was. From looms and punch cards right up to nanotech and printing buildings. We've really covered a lot of ground in this deep dive into 3D printing.
Absolutely. The sheer range of technologies, materials, it's incredible. And we've touched on the challenges, the limitations, but also the really exciting possibilities for innovation and making things differently.
So, the final thought for you, listening. How might this technology, in all these forms we've discussed, touch your life, your work, the world? Maybe check out one of those open source projects or browse a model library.
It's definitely a space to watch, constantly changing, constantly evolving. The information you sent gave us a fantastic look at its profound potential.
It really did. Thank you so much for sharing such rich, thought-provoking material for us to explore in this deep dive. It's been a truly fascinating conversation.